Hi everyone, and welcome to a new video about circuit analysis using Fourier series, and this is our example number 10. In this example we will look again to a filter circuit and we will calculate the required response and we will verify our calculations using simulations in SPICE. So again, first the calculations, then the simulations in SPICE. So let's look at our example number 10. We have the following situation. This input voltage Vin, which is shown here as a waveform, which is a Sawtooth waveform, which has an amplitude of 4 volts, and it has a period of 0.1 seconds. So it is the period of this signal that will be applied to this RC circuit, which is a low-pass filter. And the output Vout is measured across this capacitor C. The values of this resistor and the capacitor are shown here, which is the R of 10 kilo ohms, and we have a capacitor of 1 microfarads. So the question is the following: given the input signal Vin, which is applied to this RC circuit, calculate the output voltage, output signal Vout, and also the total harmonic distortion THD at the output. That is the question for this example. So let's look at our solutions. Before we move on, of course, we know that the input signal is not a pure sine wave. It is periodic, but it is, of course, non-sinusoidal signal. So we will have to decompose that as we did in the previous examples, and then we will use Fourier series to see which term will translate at the output in what condition. So first, we need to determine the Fourier series of your input signal. So if I look at my Fourier series table, I see this diagram or this figure. What I see is the following. This is just a general Sawtooth signal which has an amplitude of A and it has its own fundamental period. Now from there I just compare this to given Vin waveform, and I can then see that the A, which is the amplitude, is in our case 4, and a period, capital letter T, is in our case 0.1. So that is actually what I can see from this given waveform in the table. Now if I then look at the formula, which is then the given formula for this, then I can determine the Fourier series. So let's look at the solutions, then we will then go each of these conditions step by step. If I now look at this formula, I can see A is then, in our case, 4, so I will have A 4 over 2 in our first term, which is a DC term. This next one is A over pi, which is then the 4 over pi in our case, and then I get the summation of sine n omega 0 t over n. Now omega 0 here is actually 2 pi over that period, which is then 2 pi over that 0.1. Again, I have the sine summation from n is equal to 1 all the way to infinity. Now the n runs from 1 to 3 all the way to infinity, so it is actually just an integer. We know, again, the omega 0 can be calculated by using 2 pi over t, and I know what the A is, so I have actually all the necessary parameters for my Fourier series. Again, the fundamental period is 0.1 seconds, and the radian frequency in the general form will be given for all harmonics as omega sub n is equal to n, which is an integer, times the fundamental frequency. That can be then used for the harmonics. Now we know the omega 0, which is then the fundamental frequency, is 2 pi over that period, which is then 220 pi radians per second. Or if you want to have the frequency, the fundamental frequency in hertz, you can also do 1 over that period, or you can do omega 0 over 2 pi, you will have 10 hertz. So the fundamental frequency of this input waveform will be 10 hertz. Then, when simplified this, we will have 2, which is 4 over 2, minus 4 pi times the summation we have here. Now, as you can see, I have substitute for omega 0, 20 pi as shown here, and that runs actually using that n, and it will of course change for higher harmonics. We need to of course change it a little bit because our reference signal is cosine, so I need to rewrite this sine expression in terms of a cosine. That means actually change your expression of the cosine by a minus 90 degrees and this will result in exactly the sine of 20 pi nt. That's just a small adjustment here to have the expression in cosine. What we also can do in addition to this, because we have a minus sign in front of this summation and we have also this minus 90 degrees, we can use the following condition. We know that cosine of x plus 180 degrees is minus cosine of x. So what I use is the following. I know that minus cosine of x will result in this cosine of x plus 180 degrees. I have a minus sign outside, so I can also place this here in front of this cosine. So I have a minus cosine of this term. Then I can say, instead of using minus here, so I really want to use the plus, I can say, okay, place the minus sign in here, make this a plus. Then I have a minus cosine of this term. I can also rewrite this as cosine of 20 pi nt minus 90 degrees, which is just an x here, and then plus 180 degrees. That will result, if you simplify this, in this, because you have minus 90 degrees plus 180 degrees, that will result in plus 90 degrees inside the cosine, and you will have a plus outside your summation term, which will be of course nice to work with in the further steps. So that's actually the adjustment I have made here. Of course you can also do this in this form, which you actually prefer. So we have the Fourier series representation of our input signal, so let's look at our next steps. So we have the input signal as we have discussed. This is our input signal. We have the DC term and all the AC terms are shown here. Now, if I now rewrite this for several harmonics, first the DC term, which is given here as 2 in pink, and then I have the cosine terms, which has its own associated amplitude. So I have a 4 over pi, and over n, of course, but in this case the first one is 1, so I have 4 over 1 times pi. The next one is, of course, n is 2, that means 4 over 2 pi. Another one is 4 over 3 pi. The next one is the 4 over 4 pi. So I have just given here the first 4 harmonics. What you also see in addition is that the phase will be 90 degrees in each harmonics. This is the fundamental, this is the second harmonic, this is the third and the fourth harmonic. What you also see, what is changing is the frequency. So the frequency is first 20 pi, just the fundamental, because the n is 1. If I now make this n as 2, that will make the second harmonic will be 20 pi times 2, it will be 40 pi. 3 times is the third harmonic, will be 60 pi. N is equal to 4 will be fourth harmonic, will be 20 pi times 4 will be 80 pi. So that's actually what you have. Of course, this will go on all the way to infinity, but let's look at the first 4 harmonics and also the given DC value to have an idea what's going on actually for this signal. So if I make a table, again just looking at this n, because the k is not really interesting in the table, that will be sometimes used in another summation where the k is used here and then the n is a different expression. But in this case we just look at the n, where we have a 0, which is the DC, the 1 for the first harmonic or the fundamental. You have the second harmonic, which is n is equal to 2, 3 and a 4 for the third and the fourth harmonics. What you see, DC means 0 Hertz, the fundamental was 10 Hertz, the second harmonic 20 Hertz, 30 Hertz and 40 Hertz for the next harmonics. We know now the magnitude and the phase using this expression. Now I've just given the first 4 harmonics. You can now see that 4 over pi is the amplitude of our first harmonic. 4 over 2 pi, of course this is also 2 over pi, but I just give it in this form such that you can see that this denominator is changing only. So if I just write it out and make an approximation, that will be then 4 over pi will be approximately 1.27, 4 over 2 pi will be 0.637, and 4 over 3 pi will be 0.424, and the next one is 4 over 4 pi, is actually 1 over pi, will be then 0.318. Again, the phases are for the all harmonics plus 90 degrees. Only the DC term has a phase of 0 degrees. That is what we have now for our input signal data. And it is now easy to see what we have for each frequency. Of course, we need to determine the transfer function of our circuit. So the dynamics of our circuit are important, and the circuit was given by this RC circuit with the input and the given output, where we need the response in time domain and also the total harmonic distortion. So using phasors in a complex plane and also voltage divider rule, I can get the expression for the transfer function, which is then the output divided by the input. As you can see, output divided by the input will be the H, which is now the transfer function of our low-pass filter. Now, what is the low-pass filter transfer function? In this case, is the capacitor reactance divided by the total impedance, which is shown here, R plus the X of C. If I now use the expression for the reactance of the capacitor, which is 1 over the J omega sub n C, and also in the denominator I have this expression, simplifying this by multiplying the numerator and the denominator by J omega n C, I have this expression. Now, this is already a little bit simplified, but we can already substitute for omega sub n times omega 0, which is then n times the fundamental frequency. That is actually what we will use later on. This is the expression for our low-pass filter transfer function. So it is 1 over 1 plus J n omega 0 times RC. Now, if I substitute the values for this example, what do we have? We have 1 over 1 plus Jn, which is just the number of the associated harmonics, times the 2 pi, which is omega 0, that's the fundamental frequency, 10,000, which is 10 kilo ohms, times, this is the resistor, times the capacitor, which was 1 microfarad, which is 10 to the power minus 6. So I have now all the necessary values included in this expression. If I simplify this, I get 1 over 1 plus J 0.2 pi n. That is what we have. Now, this expression has, of course, this is a complex expression. It has an amplitude and a phase. So let's look at the magnitude, which is then given by the magnitude of the denominator divided by the magnitude of the, magnitude of the numerator divided by the magnitude of the denominator. This is actually shown here, which is, of course, discussed in great detail in the video I made about phases and complex numbers. For the angle, what you do is, for the argument, you will look at the argument or the phase contribution of the numerator, and you do minus the phase contribution of the denominator, which is shown here. So the phase contribution of the numerator is 0 because this is a pure real value and it is positive. The phase contribution of the denominator is the arctangent of the imaginary part divided by the real part, which is actually shown here. So it is 0, which is shown here in front actually, but it is of course gone, minus the arctangent of that imaginary divided by the real value. But since this is of course just divided by 1, you can also simplify it in this form. So I have now the magnitude and also the phase of this low pass filtered. So I know the dynamics actually for all values of n. So I can again generate a table like this and then see what's going on. Low pass filter circuit data. What do we have? Again, for n is 0, 1, 2, 3, 4, and the harmonics are all shown here. So that this is 0 means actually DC. The first harmonic, which is the fundamental, second harmonic, third harmonic, and also the fourth harmonic. The magnitude is 1 for DC. You can also see that from the expression very easily. 1 over the square root of 1 squared plus the n is 0 here, so that will be gone, second term in the square root. So it's 1 over the square root of 1 squared, so that's just 1. The phase will be determined by this. Now the arctangent of 0 will be just 0, so you have the phase of 0. That's what we have for DC. For 10 Hz, which is actually what you have for n is equal to 1, you just substitute for n is equal to 1. Now you do math here for yourself, you will get 0.847. The phase can be calculated using this formula, that will be minus 32. Again, if you move on for NS2, 3 and 4, you will have the associated magnitude and also the phase. This is an important table that we will use later on for the calculation of our output signal data. So let's look at our next example. That is, of course, the determination of our output signal. This is what we have for our input. Again, to refresh our memory, input signal has a DC value of 2 and the first 4 harmonics, including the 5th harmonic in this case, is also given. So it will of course go on and you will have your expression for your VN. This is the Fourier series of the input voltage. Again, the data is shown here and this is what we have just determined for our low pass filter circuit. What is now the output voltage? Of course, that is important. The output voltage is the multiplication of the transfer function of the filter and the input signal. So it is the product of these two. We know the filters and also the input voltage for the magnitude and also the phases. So we can now use this formula. That means in complex plane or in complex domain means actually the following. The V out is actually in magnitude of the filters and also the magnitude of the input voltage multiplied, and the phases must be added. That is actually what this expression means. So if I look at my magnitudes, look at DC and also the first harmonic 20 Hz, second harmonic 30 Hz, this is the third harmonic, etc. I can then calculate for each situation the magnitude of my output signal. That's just the magnitude, so the amplitude. So what do I have? I have now a DC, a value for my low pass filter and also a value for my input signal. DC value of my low pass filter was 1. The DC value of my input signal was 2, which is shown here for NS0. That means 1 times 2 will be 2 volts. So I know the DC value of my output signal will be 2 volts. That's actually the first entry here. So we will generate the table also for the Vout shortly. Vout 1, that means the first harmonic, that means at 10 Hz, and that means n is equal to 1. Again, you look at this and you will have then for NS1, you multiply that with the Vin at n is equal to 1, so it's actually the first harmonic. Again, I'm multiplying the magnitudes, you will have 0.847, which is shown here for the filter, times 4 over pi, which is then the input signal magnitude at that frequency. So that given, you can calculate this, you will have a value which is close to 1.078. That is the output signal amplitude at this specific frequency. Now, if you move on for 20 Hz, 30 Hz, 40 Hz, exact same procedure. This is all written out here. You can see that the values for the amplitudes are given for each frequency. For the phases, as said before, the multiplication of the complex plane in the complex domain is equivalent to addition of the phases. So the phase of the low pass filter, the H, must be added by the phase of the input, so that it will be added together. That will result in the phase of your output. So for each frequency again, you can determine the phases. What do we have for DC? I know at DC for my low pass filter, the H was 0 degrees. You can see that also here in this entry, first row. The first row for my input signal was also 0 degrees. For n is equal to 0, I do 0 degrees plus 0 degrees, which is very simple, 0 degrees. The next one, fundamental again, you do that for the low pass filter and also for the input voltage. You see in the second row for n is equal to 1 that the phase of my low pass filter was minus 32 degrees. My phase of my input signal, what at that n is equal to 1 was 90 degrees. So I do the math here and I will have 58 degrees. Now for 20 Hz in a similar form I will have 39 degrees, etc. So I have now also the phases for the DC and the first 4 harmonics. So I have the amplitudes and the phases, so I can now generate a table for my output signal data. Again, n is equal to 1, 0, 1, 2, 3, 4, so the DC term and also the first 4 harmonics, the frequencies, the magnitude given here, we have just calculated that, and the phases, we have here this calculated here. So I have now collected them here in this form. We can now generate the time response from there. So I have now the 0, this is just the DC value, which is this 2. The first harmonic will have an amplitude of 1.078. That will be the amplitude of my cosine term with a 220 pi t, first harmonic, and its associated phase is 58 degrees, which is shown here. So this is actually the amplitude, which is here in this table, in the red table, and I have my phase, which is also shown here next to that magnitude. For the next one, the second harmonic for 20 Hertz, which is actually this, I have then 40 pi, of course, 2 times the 20 pi. The associated gain amplitude is 0.396, which is shown here, and the phase is 39 degrees, which is also shown here. So I also made this term complete. The next one, you will look at the amplitude, which is shown here, and this is the amplitude which is then in front of this cosine term. We have 60 pi t because now 3 times the 20 pi, which is the third harmonic, and I have now also the 28 degrees, and you can move on also for the fourth one, and that will be of course go on for infinite terms, but I've just given again the DC and the first 4 harmonics to give you an idea how this is propagating. So let's then look at the next step, which is the signal spectrum, and specifically we will look at the output signal spectrum. Now this is our plot for the spectrum. We have the amplitude spectrum specifically here, and in the left side and the right side we have the phase spectrum. Again, our expression for the output signal in time domain, first term is in this case the DC term, and then the AC terms are here, the first 4 harmonics. You can see that at 0 Hertz I have an amplitude of 2, but the associated phase is 0 degrees for 0 Hertz. Again, the same frequency. If I move on for the first harmonic, which is then 10 Hertz, that is 20 pi radians per second, the amplitude was 1.078, but the associated phase was 58 degrees. And if you move on, you will see the amplitude here will be here. This amplitude for the third harmonic will be here, and this is the fourth harmonic will be here. Again, the phases, you have 58 here, 39 here, 28 here, and 22 there, and that will be of course at the specific frequency. So you have actually a pair of amplitude and phase for each frequency. That is our output signal spectrum. So what is the next step? The total harmonic distortion. So we have determined now the time response, we have seen the spectrum of the output signal. We will also look at the total harmonic distortion, THD. That's for the, of course, for the output necessary in this exercise, but let's also look at the input and then see what the effect is of the filtering by the RC low pass filter. So this was our expression for the input signal. I have now placed more terms. As you can see, I have the DC term and also the first 4 harmonics are here, and I added 3 more terms. So I have actually now in total 7 harmonics. That is purposely done because the calculation is then a little bit accurate. If I use 7 harmonics, will be much more accurate than 4 harmonics. That's the way actually to make an accurate estimation. So if I now look at the formula for my THD, total harmonic distortion for just the input, that is this formula. What is this formula actually saying? You collect the harmonics, the higher harmonics, except the fundamental, and then add them in this fashion. So you have the second harmonic squared, the third harmonic squared, the fourth, fifth, sixth, and the seventh. In this case, I just have up to 7. And you take the square root of this summation, and then you divide by the amplitude of your first harmonic, which is then 4 over pi. Then I just substitute values. What do I have? Again, 4 over 2 pi is the second harmonic, will be here. 4 over 3 pi here, 4 over 4 pi, 4 over 5 pi, 4 over 6 pi, and then 4 over 7 pi, all of them here. You square them each and then add them up, and you will take the square root and you divide by the amplitude of the fundamental term, which is the 4 over pi. That will result in 0.715, which has a total harmonic distortion for the input of 71.5%, which is a lot. Let's see what the filtering does. So let's look at the output signal total harmonic distortion. This was for the output. I've then again used more terms to have an accurate estimation, because we will also simulate this and we will check what the calculations and the simulations are correct. So we have again the DC term and also the first, second, third, fourth, fifth, sixth and the seventh harmonic. So I also have 7 harmonics plus the DC term here for my output signal. Again, in a similar form, I can calculate the total harmonic distortion just for the output, so THD out, and I look at the V out, the second term, third term, fourth, fifth, sixth and the seventh term. Each of them will be squared, add them up, and then you will take the square root. You will see that here. This is the amplitude of my second harmonic, which is shown here. This is my amplitude of my third harmonic, which is shown here. This is the amplitude of my fourth harmonic, which is shown here. This is for the fifth, the sixth and the seventh harmonic. I will divide that by, just using this formula for the numerator, I will divide it by the amplitude of my first harmonic at the output, and that will result in 0.436. Now in percentage it will be 43.6%. You can see the decrease in the distortion, so the filtering does have effect on the shape of your signal. That will be a little bit smoothed out, so you will have less distortion. That's actually one of the reasons why you will filter out your input signal or the given sensor signal, for example. Okay, that's actually what we have for the calculations. Of course, we need to simulate the results and check what we have. First, before we move on, let's also look at the body plot just specifically for our filter. This is the 10K for our resistor and a 1 microfarad for our capacitor. That's the input voltage, the output voltage. So we have plotted here the body plot, which is given here the frequency in log scale. So you have the 0, 0. This is the 10 millihertz, 100 millihertz, 1 hertz, etc. Of course in log scale. And you will see the magnitude given in amplitude, so just scalar, not in dBs. This is the phase given in degrees. So you'll see it starts at 1, and then it decreases. And at 10 Hz I have this gain, at 20 Hz I have this gain, and at 30 Hz I have this gain, 40 and 50. So I have actually seen also this in our table. So this is really very accurate what we have also in our table. But you also see the phases. So I had here also, it's very similar results. So we'll see that the calculations and the simulation data do match very well for the body plot. The simulation result for the transfer response are also very important, because that will determine the shape of your signal and also the Fourier series. So this is the input signal, the blue one, which is of course what we have applied. This is the amplitude for, and I have a period of 0.1 seconds. So that will go on, go on, go on. You will see that the first period, or the first section of the output signal, which is given here as the dark red curve, is of course the transient effect. So in order to determine later on the Fourier series, we have to look actually a little bit later on, after for example 0.2 or 0.3 seconds. And that will be of course a little bit smoothed out. So that is also the reason why we have a little bit smaller THD here for the output than the input. That's the transient response, and we will use this transient response figures to determine then the Fourier series by post-processing this in the SPICE. So Fourier series and the THD. This is again the circuit in the simulator. This is the given signal waveform for the input. This is the given circuit in our assignment. This is our Fourier series for the input. I already said that we don't start at 0 0 seconds, so a little bit later to have the transient effects actually not taken into account for our Fourier series, but will be of course have an error in our calculations because we want to have the steady state section. So we start at 20 milliseconds, so a little bit later after the transients. The base frequency is in our case 10 Hz, so that's actually what you have here. Number of samples is how accurate you want. I've just selected here the largest one. Number of harmonics I want to plot is 7, and this is the way I plot here. This is the amplitude and this is the frequency, and this is the phase of the associated harmonics. In this case, I said it also in the previous videos about simulations, this simulation program uses the K actually as the harmonics. So in our case, what K is actually N. So if you read here the K, it means actually N. That's actually the only change we need to make. So the amplitude, the phase, which you see is 2 volts is the amplitude, and the associated phase was 0. That was also the case for us. So if I look at the input, which is also shown here, you can see that the 2 and a 0 phase orientation. 4 over pi was the first harmonic, which is then 1.27. You can also calculate that approximately, is it? And you can see that this is really close to 90 degrees, which is actually what we have also for the first term. Second term is 637 millivolts approximately, which is actually this, if you do the math here for yourself, and also again 90 degrees. And that will move on, and you will see that the phases will stay approximately 90 degrees. This error is just due to that simulation numerical error. So, but actually, in theory, it must be exactly 90 degrees. This is for the input. And you can also see that was the calculation for the total harmonic distortion. It was now 17.5%, which is very close to what we have calculated. Now, let's also look at the output, which is then this diagram. Again, we started a little bit later, 200 milliseconds, and this is the base frequency, 10 Hertz, and again, a number of samples, and also 7 harmonics. The same format, but just looking at the Vout. Vout was here, given, again, the DC and the higher harmonics, and the fundamental, second, third, etc. You will see, again, the DC is 2 at the output, and it will have a phase shift of 0 degrees. You can see that this will be 1.078, and approximately is it 1.08. So this is very close to what we had. The phase is here 58 degrees approximately, and you can also see that in the calculations. The next one, for example, this, it will be 396 millivolts. That's actually what you see here approximately, and the phase must be approximately 38 or 39 degrees. And what's actually what we have. So it's just a very small error that is just due to the rounding off errors here and also numerical errors in our simulations. So if you move on for the next terms, you will also all of them see here, and also the associated phases are very close to what we have calculated. So this is the calculation, this is the simulation, this is the calculation for the input, and this is the simulation. You can see that the simulation data for the output signal and also for the THC, which is this for the output signal, also do match very well, because we had a very close value to 43.6 degrees. So you can see that the calculations do match also in THD. If you of course take larger values, for example up to 11 or 16, I think it will go up to the 16th harmonics. You will have of course a little bit accurate value for your harmonics, but that is not really necessary if the higher terms really don't contribute that much. You can also see that at the output, the first one is 1.08, and the next one is approximately 400, and then approximately 200, and approximately 118. But you will see that it is really decreasing very rapidly. For maybe the 8th or the 9th harmonic, that will be of course much smaller, and that will not contribute that much. And so you can actually neglect that and have a very good estimate by looking at several harmonics, not infinite harmonics. So that's actually for this exercise, this example number 10 about a RC low pass filter, where we have used the sawtooth input with its own period in the amplitude, and we have seen what the response is for this input for our RC circuit. Again, the input is given, the output is given, the THDs are given, and the Fourier series are given in the simulations. Okay, that's for example number 10. I will see you next time in a different video, and I will try to also do design examples where we use the Fourier series to design a specific circuit. So keep in touch, and if you have questions, please let me know. Take care and see you next time.